Hey y'all, welcome back to another round of physics. And as promised, this video will deal mainly with the moment of inertia of an object. So let's go ahead and take a moment and identify how do we actually do the moment of inertia for continuous objects. So continuous objects. In other words, ones that we don't have as discrete masses. So for an example, let's go ahead, let's take a very thin bar. So we'll make this a really thin bar that has some distance L. So we'll call it capital L, and it has a mass of capital M. And for sake of making it easier for right now, let's go ahead and assume that it's uniform mass density. In other words, lambda will be equal to M over L. So let's go ahead and let's calculate the moment of inertia about the center point, right there, right in the dead center. And the question is, how do we go about actually setting up this equation and solving it? Well, you know the basic idea. I still need to take each of these individual masses, and for each individual mass, I will calculate the quantity m r squared. The only difference is that now it's an infinitesimally small mass, so I'll call it dm. And rather than doing the summation, because they're infinitesimally small, we'll do the integral. Same idea, it's just they do different notations to represent discrete versus continuous. So this is what we actually need to do. Now taking my rotation axis to be right here, and I'll go ahead and set the origin at my rotation axis, or the pivot point. That means that r, I'll call this direction, I will call x. And that means that I need to take the summation from negative L over 2 to positive L over 2. Furthermore, because it's a 1D object, my r is going to just become x. So let me rewrite this. I'll have something like I is equal to the integral from negative L over 2 to positive L over 2 x squared. And now I need to come up with an expression for this little infinitesimal chunk of mass that I've called dm. Well, we have the linear density. And if I take the linear density and I multiply by a small distance dx, you'll notice the small distance dx cancels with the L. And evidently, I will end up with a very small mass, just a portion of the total. So that's what I'm going to write down here. I'm going to write this as m over L. And I can do that again because the distribution was uniform, times dx. And there is the expression that I actually need. I need to integrate this. Fortunately, you notice that this is constant. So I can pull that out. And so I get something that says equals m over L, integral from L over 2 to L over 2. So negative L over 2 to positive L over 2, x squared dx. The question then becomes, what function, when you take a derivative, do you get x squared? Good, 1/3 x cubed. So evidently we have m over L times 1/3 x cubed. You can see if I take the derivative of this, I end up with x squared. And I need to evaluate this at two spots at the endpoints, L over 2 and negative L over 2. You don't need me to do this. You've got it yourself probably. I is equal to m over L 1/3. We have L over 2 to the third minus 1/3 negative. That negative sign is really important here. L over 2 to the third. And I'll do a close bracket here. There we go. So at the end of the day, we have m over L well, let's see, 2 to the third is 8 times 3 is 24. So I have L cubed over 24. And you notice, okay, 2 cubed, negative 2 cubed is negative 8. So I have negative 1 over 24, and then I subtract it, which means I get a plus cubed over 24. Ta-da! This is the moment of inertia for a thin bar rotated about its center of mass. Pretty cool. And if we look up in a chart, which I'll have to post at the end of this video, we'll see that indeed this is the right value. Cool. Well, let's go again. Again, more. Oh, yes. Why don't we go ahead and we try a different scenario. Same bar. We'll do a thin bar. And what I'm going to do is, let's say now, instead of doing it about the center, let's go ahead and rotate it about one of the ends. Take a minute, go ahead and set up the equation. You got it? Say, I'm still going to use x since we're dealing with 1D, so we still have x squared. We still have this m over L, right, representing the mass, m over L dx, representing the mass of that little chunk there. And hopefully you see the only thing that changes here is that now my limits need to change. I go from a value of x equals 0 for the little mass that's right there on the rotation point to the mass right out here, which is at x equals L. So I got to sum all the way between those two locations. Well, I'm sure you're already off and rolling like a herd of turtles. Bale the turtles. Should have something like this. Right? We've already done this antiderivative. This is just a constant, so we just pull it out front. Boom, we've got the answer right here. And the only thing left to do is to evaluate it. So, well, let's see. We have ml squared times 1/3. That's evaluating at the L. And of course, you notice that because we have x, we're multiplying by x. When we put 0 in, we're going to end up with 0. So here is, again, here is the moment of inertia for a 1D thin bar rotated about an endpoint. Okay, so how about this? Let's do the moment of inertia of a rectangular plate about the center. So a rectangular plate about center. Okay. Well, let's go ahead. I'll just draw a quick sketch. Very rough. We'll call this distance A. We'll call that distance B. And we need two distances. And we're going to rotate it about an axis through the center of the plate. Okay. And again, we're doing the same idea. Let's say I've got a little chunk here. Okay, right there. I need to know what's the moment of inertia of that little chunk about this rotation axis. Oh yes, let's say the plate has a mass of m. So the first thing I'm going to do is let's see if we can come up with an expression for this little chunk. And I will call, I will call this direction x. I'll call, up. I guess I'll call y. And out of the board, or out of the page, I'll call z. So we're going to be integrating in the x and the z direction here. Well, what I would first start off with is sigma is equal to m divided by AB. In other words, let's assume that the plate is uniform. Maybe I should say it's uniform. And because it's uniform, I can take that whole mass and divide it out by the entire area and get an areal mass density. Okay. Well, you know the song and dance now. I want to find the moment of inertia, and that's going to be equal to the integral of r squared dm. And I just need to come up with some expression for dm and r squared. Go ahead, take a minute. You got it? Rock and roll. So because I have the sigma, what I'll do is, let's think about it. dm would simply be my infinitesimally small area, which I will represent as dx dz times sigma. So you notice now I have to do a summation not over one direction, but two. And this is sometimes referred to as a double integral. So now I've got two of these because I've got to do it over the x direction, I've got to do it over the z direction. Okay. Well, hopefully you see the distance is just going to be given by x squared plus z squared. Let's say, okay, well, this piece is a distance x from the rotation axis, and it's a distance z in this direction. So I must need to find the hypotenuse of the triangle, which is x squared plus z squared square rooted. And then I take advantage of the fact that the r is also squared. So I get x squared plus z squared times sigma dx dz. And the last thing that's left to do is we need to figure out what are the limits of integration here. I need to do this from what distance to what distance. Now, to let you know, commonly what happens is the first infinitesimal length is associated with the inside integral sign. So you work away from inside outwards. So if you wanted to, most mathematicians and even physicists, we're all lazy. If you wanted to, wow, you could think of taking that middle one and putting a parenthesis in, like this. So you do the inside one, then you do the outside one. Most people won't put those parentheses in. Okay. Well, let's take a look at what we have here. So if x goes a distance, x represents a length of b. Evidently, we must go from negative b over 2 to b over 2. Similarly, the z goes from a distance of a over 2 to a over 2. Okay. Now we just do the integration. So the first one, since z and x are independent, we can go ahead and we can just integrate. So what we get here, well, first off, we do the inside integral first. So we have negative a over 2 to a over 2. We'll pull the sigma out since the sigma is a constant. The antiderivative of x squared. So what do we have to take a derivative of in order to get x squared? Well, that would be 1/3 x cubed. And the derivative of what will give me just plain old z squared? Well, that would just be x times z squared. There we go. And of course, we need to evaluate this at negative b over 2 to b over 2. And once we do that, then we do dz. Okay. Now I'm being careful here. There are sometimes right here, okay, notice that these are both constants. But as you progress in your calculus career, you'll find that sometimes you can set this will be a function of z. So then it'll be very important to do the evaluation before you do the next integral. Okay. Here you could actually do both integrals right away and then just do the evaluation at the end. I'll be more not rigorous, but I'll be slower than that. So we have negative a over 2 to a over 2. 1/3 times b over 2 cubed plus b over 2 times z squared. So that's just evaluating at the upper limit. Then we need the lower limit. 1/3 negative b over 2 cubed plus negative b over 2 z squared. Of course, we still need that dz in there. And this looks like a mess, but notice I have a minus and a minus. Okay. And actually that minus is here as well. So what I end up with is, notice that this is going to be added to that. This will be added to that. So I have 2. So I'll just pull 2 sigma out. But wait, we still have to evaluate that. So that being the case, well, we've got this. Step 2 is now commencing. Let's go ahead and integrate that. And of course, let's see here. You get 2 sigma. Here we have b cubed over 24 z plus b over 6 z cubed. That would be evaluated at a over 2 to a over 2. Now let's go at it. 2 sigma. We have b cubed times a, all divided by, let's see, 48, plus b a cubed over, well, 2 cubed is 8 times 6 is again 48. Oops, excuse me. That's evaluating at the upper. And again, you'll notice if I write this, I'll get b cubed a over 48 minus b a cubed over 48. And again, I've got a minus, minus, minus. So these would be pluses. So I've got 1 b cubed a over 48, 2 b cubed a over 48. And we're in the home stretch. You say, oh, goody, goody. The 4 cancels the 48. This becomes 12 for each of these. So we can pull that out. And here I'm going to substitute back in what sigma represents. So I get something that says m over 12 ab times b cubed a plus b a cubed. Oh, goody, goody. The ab cancels. I get a 2. I get a 2. So what am I left with at the end? I get something that says, well, the moment of inertia of a rectangular plate about the center is simply a squared plus b squared times m over 12. Well, I'll call it there for right now. That's a pretty long video. I say take another look at it, keep going at it. Thanks for your attention. I'll see you soon.